Inequalities are our way of describing the relative positions of two numbers on the number line. We can talk about things being less than or equal to, greater than or equal to, strictly less, strictly greater. Now, an important principle that we are very used to when dealing with equalities is the following. So this is equalities. I want to think about equalities for a moment. So that's when two things are completely equal to each other. So key property of equalities. So a key property of equalities is the following. If two quantities are equal, so completely the same, two things are totally identical, 5 equals 5, then applying the same operation to both preserves the inequality. Preserves inequality. Or preserves equality, sorry. All right. It's a really foundational principle in mathematics. Really foundational. So if two things are exactly the same, if I do the same to both, of course they stay the same. Right? It's one of these things that you never really consciously think about anymore because it's so kind of drilled into your mind. Just as a quick example, really simple example, if I was to take A equal to B, that guarantees, well, if I square both sides, they have to remain the same. So a really key principle. Two things which are equal, if I do the same thing to both, they remain equal. Warning. This is a major warning. In general, this is not true for inequalities. This is not true for inequalities. So you may have an equality between two things, an inequality. Do the same thing to both sides, it may change the inequality. So as an example, let's use this square example, shall we? It's in front of us, so it seems sensible. So 1 is less than 2. Okay, and, well, 1 squared that's equal to 1 is certainly less than 2 squared. So in this case, squaring preserves the inequality. The direction remains the same. So maybe I'll say inequality preserved. However, imagine if I was to choose this instead, minus 2 less than minus 1. Well, in this case, if I square both sides, what happens? Well, it's now 4, and it's 1. So the inequality is reversed. Thorny. So this tells you immediately doing algebra or things which involve inequalities is going to require significantly more care than doing algebra with equalities. So that's the conclusion we should draw here. Must be very careful. I do stress very here. Very, very careful when doing algebra with inequalities. It is absolutely not as simple as, well, you've got an inequality, do the same thing to both sides, the inequality stays the same. So I think to begin with, we should focus on our most basic algebraic operations. And the two most important algebraic operations really are addition and multiplication. Remember, subtraction and division are just those interpreted in a slightly different way. So let's think about addition to begin with. So as I said, this will contain subtraction as well. So I think we should do this visually, because it's by far the best way to think about inequalities. Okay, so I've got a number line, and let's assume for a moment this is the setup. So let's assume this is my A, and this is my B. Okay, so let's imagine so in particular, in this situation, what do we have? We have A is less than B. Okay, that's the setup I've come from here. Well, what happens if I add something to this? So if I add something to it, positive, what will happen? Well, it'll shift everything to the right. So let's imagine I have an addition of both things to C. And let's assume it's greater than 0. So it's going to shift everything up here, isn't it? So what you're going to end up, you'd end up with A plus C, and you'd end up with B plus C, just kind of over here, wouldn't you? And what happens? Well, we've still got the same inequality, right? They are still preserved. So up here, the inequality is preserved. A plus C is still strictly less than B plus C. Very nice. What if I was to take away? So if I was to do minus C, where C is positive, and that's really just plus of minus C, so that's why I'm not bothering thinking about subtraction. But if I do minus C, well, everything gets shifted down. What happens? Well, you'd end up with A down here, given an A minus C, and a B minus C, and the same story holds, okay? That's still that. So maybe just to make this nice and neat. Yeah, let's do this. This is a nice way to draw it. So again, the inequality is preserved. So just as a quick numerical example, I don't know, 1 is less than 3. This implies, I don't know, let's add 3 to both sides. Yeah, 1 plus 3 is less than 3 plus 3, which implies that 4 is less than 6. We could write this the other way around. It wouldn't make any difference. 4 is strictly greater than 2. So let's take away 5 from both sides. 4 minus 5 is strictly greater than 2 minus 5. So that would imply that minus 1 is strictly greater than minus 3. Correct statements. So addition, or indeed subtraction, the same thing, basically preserves the direction of the inequality. That's very nice. Let's think about multiplication. Or indeed division, that's part of it as well, but let's think about multiplication. Okay, so I'm going to think about multiplication a bit more seriously than I have addition. Addition is kind of just translating what is multiplication. So let's draw another number line. And this one I'm going to be quite a lot more careful about. Okay, so let's have 0, 1, 2, 3, 4, 5, 6, 7, ... Let's do minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, ... Okay. So let's take a moment to think about multiplication quite carefully, shall we? So the first thing is, when I multiply, what am I really doing? So let's take a super duper simple example. Something so simple that it kind of looks ridiculous. But imagine I take the number 2 and I multiply it by 3. And I ask myself, what's that equal to? So here's a nice way to think about multiplication. So let's draw kind of an arrow, if you want, between 0 and 2. So this is kind of length 2, if you want. Now, what does 2 times 3 mean? What it really means is taking this arrow and stretching it or scaling it outward from 0 by a factor of 3. So it's like taking this guy, so this is going to be a bit weird because it's going to get bigger. It'll get wider when it shouldn't do. I'm only going to stretch it out, but it's kind of like doing the following. Taking this guy and stretching it out like this. It shouldn't get wider, it should only get kind of longer, but that's the idea. So multiplication by 3 should be taking this and scaling it by factor 3, making it 3 times as big. Okay, so let's kind of draw that with a different color. So when I multiply by 3, what's it doing? It's going to go out to the position. What's this all about? How annoying. It's going to go out to the position out here, is that right? So this is scaled outward from 0. Kind of stretched, if you want. Outward from 0 by a factor 3. It's kind of a nice way of thinking about it. You could think about it as just laying 3 of these on top of each other, or end to end, but this doesn't only have to be for whole numbers. This could work for anything. Okay, so this position at the end is exactly what 2 times 3 is. So where are we? This position here. This is 2 times 3, and of course it's equal to 6. All right. What about multiplication when I'm dealing with negatives? So this really crucially relied on the fact that this term here is positive. Let's think about the same basic story, but with 3 times or 2 times minus 3. This is kind of an interesting exercise. We're taking a really familiar concept and trying to really, really dig down into what it means very, very carefully. So let's go through the same basic story. So I've got this guy down here. Well, what does it mean to multiply by minus 3? Well, it means 2 things. So first of all, minus 3 is negative. So minus 3 is negative. And that makes multiplication quite different. When you multiply by a negative, 2 things occur. So the first thing that occurs is you take your 2 and you scale it, just like you did before. Okay, so you take something like this, exactly the same. So you'd scale it out by 3, outward from 0. But then because it's negative, what do? Well, you reflect across 0. So you take this guy basically and you reflect it across. Let me try and draw this in a reasonable manner. So if you reflect it across, you'd be drawing it out in this direction. I'll try and make this neat. So it'd be reflected out back to here. So multiplication by minus 3 is kind of doing 2 things geometrically. Like I said, it's scaling. It's scaling exactly the same as before, scaled outward from 0 by factor 3 and reflected across the origin. Reflected across 0. Something I will say is this reflection business, you could interpret it in a slightly different way, which turns out to be a good idea in later courses. But once I've stretched it out here like this, you could think about the reflection as the same thing as a rotation by, well, 180 degrees around. They're the same thing when it comes down to it. That turns out to be a good thing to do. a little bit later on, but it's the same as reflecting across 0. So that's a good way to think about it. So what are we left with? Well, this position here, here's exactly what we're looking for. It's 2 times minus 3, which is equal to minus 6. So multiplication by a positive is taking your first number and stretching it out from 0 by that scale factor. Multiplying by a negative is doing two things. It's doing the same scaling, but then it's reflecting across the 0. So this is a really very detailed look at what multiplication means. Let's consider what this means for inequalities. So what does this mean? For inequalities. What does it mean for inequalities? So I think we should do it by example. Let's take the following picture. So let's start off with some positions in the number line. So let's have 0 here in the center. And let's have what? Let's have minus 1 here. And let's have a 2 here. Let's try and make it a reasonably good scale. So we'll do it like this. Minus 1 and a 2. Okay, so in particular, minus 1 is less. So what do we have? Minus 1 up here. Minus 1 is strictly less than 2. Now, let's do the business of multiplying by 3 or minus 3. Now, if I multiply by 3, what happens? So let's multiply by 3. So let's take the number line again. I take the number line again. And I've got my 0 kind of dead in the center. But then what happens? Well, the minus 1 and 2 are stretched out. They're scaled outward by a factor 3. So that means minus 1 would move in this direction and 2 would move in this direction, wouldn't they? Right. So you'd end up with what? You would end up with your position minus 1 times 3. Okay, it's minus 3, of course. And then you'd end up with, further out here, 2 times 3. Shouldn't write a bracket, there's no need. So again, what are we doing here? We are scaling outward. By a factor 3. Scaling outward from 0 by a factor 3. And what do I see? Well, the inequality is preserved. Right, it's the same thing. So of course this is equal to, where am I? So minus 1 times 3, it's minus 3, but I won't bother to simplify it, is equal to, oh sorry, it's strictly less than 2 times 3. So in other words, the inequality is preserved. Okay, nice. So multiplying by this positive preserves the inequality. What happens if I multiply by minus 3? So multiplication by minus 3. Well, now it's quite a bit more confusing, right? Because multiplication by minus 3 isn't just this stretching out. It's also doing this reflection across 0. So when we stretch out, everything's fine, the inequality is preserved, but when I reflect across 0, it's going to flip the positions. So for example, 2 times minus 3. 2 times minus 3 would be, so first of all you'd have a 2 there, you'd multiply it by 3 to get out there, but then you'd reflect across, so it'd end up back here. So you've got a 2 times minus 3 here. And then on the other side, what's it going to be? Minus 1 times minus 3. So you'd have a minus 1 stretched out by factor 3 or whatever it is, and then reflected across. So it's back over here. So this would give you minus 1 times minus 3. Of course, it's equal to 3. So again, what are we doing here? Let's make sure we really understand. This is two things. Scale outward by factor, scale outward with a factor 3. So scale outward from 0 by factor 3, and then we reflect across 0. Now what do we see? Well, now what we see is everything's reversed. So the inequality has been turned around, if you want. So what do I see? What's a nice way to write this down, to flip it? It would be, it would be now 2. I'll write it in the same way, right? Now what do I have? I would have minus 1 times minus 3 is positive now. 2 times minus 3. It's minus 6, of course. And now the inequality is reversed. So what's the conclusion here? Just looking at this example, we can see the general story. So the conclusion is multiplication by positive, it preserves the inequality. Whereas multiplication by a negative reverses it. It reverses the inequality. So we've not completely justified by that, or not justified it, sorry, but it's pretty obvious that it's true from this specific example. Whoa. Okay, so to conclude, addition and subtraction don't alter the inequality. It stays the same. Multiplication is much more delicate. Multiplication by a positive preserves. Multiplication by a negative reverses. And next time we're going to look at much more detailed properties of inequalities.